Okay, so moving on to not just thinking about the sort of shapes and orientations of these orbitals, but now thinking about how their energies stack up in an atom, ultimately getting to this position of how do electrons actually arrange themselves if all of these orbitals are available to them, which is based on energy, right? All things in the universe move from low energy to high, so we need to sort of rank all of the orbitals by their energy, and then when we know how many electrons an atom or an ion has, we can just fill them up from low to high. But that requires a little bit of hand waving to get there. So for a hydrogen atom, as we've sort of talked about in the simplest case, a hydrogen atom only has one electron. And in that case, the principal quantum number defines the energy of that electron and its orbital. And so that's really easy. But we know that everything on the periodic table except for hydrogen has more than one electron, in which case we can't negate how electrons actually interact with each other, because we have these two negatively charged things. Whether you think about them as particles or waves, there's still going to be some sort of repulsive force that exists between these. We call these Coulombic repulsion, from the word Coulomb, which is the unit of charge. You may have learned this in physics, but you'll learn it again in Chem 2. So what I've got is a sort of pictorial representation of exactly that. So for multi-electron atoms, we can't negate the fact that this process, this repulsive and attractive force, is going to occur. And so the actual energy levels, we're thinking about these lines here, these orbits as the orbitals, even though we know that's a totally improper way to think about it. In this representation, we're just thinking about it because it's easier to represent, but we know it's actually a quantum mechanical description. So the actual energy levels, if we're to sort of plot the energy levels of all of the orbitals, maybe 2s and 2p and 3d, etc., exactly where those exist in the ordering, it's a complex interaction between these repulsive forces inside of the atom and between electrons within them. So you got two really sort of predominant forces here. You've got the repulsive force that I mentioned. So you've got an electron in one orbital here, and if it's close to another electron in another orbital, it could repel, in which case that's going to raise the energy of these things. Repulsive forces aren't good for stabilizing things, so the energy goes up for these things. But at the same time, you've got electrons that are in the outside perimeter of this really large positive center. Why is this positive? Well, it's where all the protons exist and the neutrons, but neutrons don't have a charge. So you've got this really dense positive center, and then all these negative electrons that are in standing waves around it. And so there's this attractive force, this net stabilizing force pulling it inward. And so there's a balance of forces between attraction and repulsion that give rise to the actual specific energy levels depending on how far away these electrons are from that nucleus. And so we have to introduce this sort of new parameter. And so the outer electrons here are essentially effectively shielded by the inner electrons. If you think about, let's do this in green, think about this outer electron and let's compare it to, say, this inner electron. So if you think about, this is a point charge in the center of this nucleus, this positive charge. It's got a certain amount of positive charge. If there's a whole layer of negative charges here, all sort of attracting, how do you think that positive nucleus is being felt the further you get away from it, especially if there's a bunch of negative charges that are canceling out some of that positive charge? Well, hopefully the intuition is that the further you get out here as an electron, and there's more electrons between you and the positive center, that becomes what we call shielded. It's got an effective less positive charge here than it does here, just because some of these electrons have canceled out some of that positive charge. So we define this new term called Z effective, or Z sub EFF, and that Z is referring to the charge here, the number of protons, but the effective charge is whatever the charge is as you get further and further out from the core of that nucleus. And so the Z effective is going to be the actual Z being whatever is felt immediately at the nucleus, right here at the core, minus whatever the effect is from the electron shielding, which is a function of how close those electrons are and how many are in your path. And so it's really this idea of Z effective and shielding that gives rise to some sort of maybe not so intuitive rankings of orbital energies as we go from low to high. Okay, so this takes us to actual electron configurations of an atom. An electron configuration is how electrons fill orbitals, available orbitals, from low to high energy. And obviously that requires us to know what the energy of those orbitals are, which is a function, as I mentioned before, of the effective nuclear charge. The way that we think about an electron configuration and how we fill these is largely dictated by this principle called the Aufbau principle. And Aufbau is German for filling up. So it really literally means filling up the orbitals with the electrons. So the Aufbau principle states in sort of the first way, which is pretty intuitive, that lower energy orbitals fill first. So lower energy orbitals get the electrons, fill electrons first. We also know from the Pauli exclusion principle that each orbital can only hold 2 electrons, and they have to have opposite spin, that spin quantum number ms. And that came from the fact that without this, then we would have electrons with redundant sets of 4 quantum numbers, which we can't have. 3 orbitals that are degenerate, and I'll tell you what degenerate means here in a second, just bear with me. Orbitals that are degenerate. Degenerate means same exact energy. How do we fill those? So that's things like a px, a py, and a pz. They all have exactly the same energy. How do we fill them? So we fill each with 1 electron to start with, until each has 1 electron in it, and then we pair each single electron 1 at a time with the opposite electron spin. This will make a little bit more sense once we actually do an example. Each electron in a degenerate orbital has the same spin. So for example, if we have 3 degenerate orbitals and we're going to fill them up 1 at a time, as is mentioned in this first case, they're all going to be spin up to start with. We're not going to have 1 in spin up, 1 in spin down, 1 in spin up. They'll all be in the same spin configuration as we first fill, and then we pair each single electron with the opposite spin. So if we add more electrons, then we're adding and pairing with the opposite spin in this case. We call sort of this principle here, this idea of filling it up 1 at a time and pairing later, some people call or refer to this as Hund's rule. And this makes some intuitive sense that if you've got 3 degenerate orbitals and you're trying to figure out how to fill these up, it doesn't make sense to pair your first 2 electrons up like this, because now you've got 2 negatively charged particles really close to each other in the same subshell. It's better if you've got 1 in one and another in another. That's going to be the furthest away, meaning it's going to minimize its repulsive or coulombic energy, and this is going to be a lower energy configuration. So Hund's rule is exactly this. Fill each degenerate orbital one at a time, all spin directions the same, and then pair as you go from there. Okay, so what does that actually look like when we're filling these things up? Well, if we look at boron to start with, boron, and I'll show you a periodic table here in a second. Boron has 1s, 2s, and 2p orbitals. It's got a total of 5 electrons. We know that it has 5 electrons because it has 5 protons and it's a neutral atom. So remember from chapter 2, if it has 5 protons, it has to have the same number of oppositely charged particles. It's got 5 electrons. We know that the energy is going to increase with the principal quantum number, and so we can start with the 1s orbital, and that's the only orbital within the principal quantum number 1, remember from earlier in this chapter. And so then we move to the next principal quantum number of 2, and we can have L equals 0, and we can get 2 electrons in there, and we can have L equals 1, and we only need to fit 1 electron in there. And so this would be the electron configuration that we would write out for boron and the corresponding orbital filling diagram, meaning we would take the 1s, we would fill it with opposite spins, the 2s with opposite spins, and then we would take the 2p, which has 3 degenerate orbitals, because these are m sub l equals -1, 0, and +1. Doesn't matter if you put this as spin up or spin down, you just want to be consistent as you start to fill this diagram going forward. Okay, we've got a periodic table here now. Let's just double check that against our first example here, boron. So boron is all the way over here. So we can see that boron has this atomic number of 5, so Z equals 5, which means it's got 5 protons, which is how we deduced it had 5 electrons. And then we, just knowing what we know about the quantum numbers, we know that the energy level is set by the principal quantum number, so we know that n equals 1 has to be lower than n equals 2, or we're adding through the Aufbau principle from the lowest energy to the highest energy. Okay, so for a carbon, we're jumping over 1 on the periodic table. That's got 6 electrons because it's got a atomic number of 6. So it's exactly the same as boron. It's just got that 1 extra electron. So we're going to fill up this whole section exactly the same way as we did with boron. So 2 into the 1s orbital, 2 into the 2s orbital, and then 2 both spin up in the 2p orbital. So Hund's rule is operative here, where instead of pairing this like this, we're putting it in its own degenerate subshell. Nitrogen, jumping 1 over, same thing. Now we've got all 3, 2px, 2py, and 2pz, and we're just adding in that 1 extra here. So we're going to do a bunch of examples just to walk through this. So a handy way to think about how to fill rather than sort of memorizing 1s1, 2s1, etc., is we can use the periodic table, because the periodic table is really telling us the electronic structure. And so here I've got a table that's highlighted based on the specific electron configurations, but let's just go through it. So if we're starting with hydrogen, hydrogen's got 1 electron. And that means it can have the very smallest, lowest energy orbital available to it, which would be principal quantum number of 1 and a angular quantum number of 0. And m sub l also has to be 0 because it can't take on any other values, which means that that 1 electron gets filled into that 1s orbital, which means that hydrogen has an electron configuration of 1s1. Right? If we continue across the periodic table all the way to helium, remember each subshell orbital can take on 2 electrons. So if helium has 2 electrons, because it has a atomic number of 2, so it's got 2 electrons, then where does that extra electron go? Well, we still have room in the 1s orbital, so that means this is going to have a 1s2. configuration. Okay, so this would be the n equals 1 row. Now we jump down. Because we can't have a 1p orbital. Why can't we have a 1p orbital? Well, our L value is constrained by the fact that it can only be up through n minus 1. And if n is equal to 1, L equals 0, that means we can never have an L equals 1 for a principal quantum number of 1. So that's done. We're done. 1s2 is the only orbital that can exist with a principal quantum number of 1. So that means we jump down, and the next highest energy orbital that we could equate would be something with n equals 2. So what's the lowest energy configuration of an orbital with a principal quantum number of 2? Well, if it's got a principal quantum number of 2, then L can take on either 0 or 1, which means we could have s or p orbitals. S orbitals are always going to be the lower in energy first because they have the least number of nodal planes in them. And so as we're filling up electrons, now we've got lithium. It's got 3 electrons. So we're going to fill up the first 1s1, 1s2, and then we're also going to fill up the first 2s1. So lithium is going to take on 1s2, 2s1. Similarly, beryllium's got 4 electrons, so beryllium's going to take on 1s2, 2s2, because we've got an available slot in that 2s orbital. So we can traverse across here over to boron, and this is where we tack on the next orbital, right? Because the 2s orbital is full up. Can't fit anything more into it. So what's the next highest energy orbital? Well, the only thing we have available left within the n equals 2 shell is the p orbital. So if the p orbital is available, remember we've got 3 different m sub l configurations of p. We could have the -1, the 0, and the +1, which is equivalent to the px, the py, and the pz. They don't have to necessarily correspond with these, but we have those 3 different shapes of orbitals, and we can fit 2 electrons into each one of those, which means that if we get to boron, we can stuff that 5th electron into the first 2p. Carbon, we can go into 2p2, nitrogen 2p3, oxygen 2p4, fluorine 2p5, and then neon gets this nice 2p6. So we've rounded it out. We've packed everything we can into the n equals 2 shell. That means we need to jump down a row, and we've got to expand our shell to the n equals 3. And this continues, right? So now we have, at the n equals 3 level with sodium, let's write out sodium down here. Sodium has got its 1s orbital completely full, so there's 2 in there. It's got its 2s orbital completely full, right? And then it has its 3s orbital, that's the next available one, and it's got that 11th electron there, which makes it different from neon. It's that extra one that's going to sit in that 3s, and that would give us what our sodium electron configuration is. We could write this out showing the orbital configuration too. We have our 1s, our 2s, oops, I'm sorry, this should be 2p6, 3s1, 2p, and then 3s, and we could fill these up. So there's our 2, 4, 6, 8, 10, and then that bonus goes on there. We can continue as we move across. This gets us to the 3p set, and then we go down here to n equals 4. Okay, so at the n equals 4 level, it gets a little bit different. So let's take a pause here. So there's a nice shorthand way of writing this as well. So instead of having to write out necessarily this whole series of all the subshells, sometimes that's nice, sometimes it's not necessary. What we can do is write out just what the closest or the nearest closed subshell was, and then tack on whatever the additional new subshell was. And so in the case of sodium, if we identify sodium right here, by close to subshell, I mean what was the last full principal quantum number shell that was completely filled up before we transitioned to the next level. And so if we look, we went from 2s2, 2p6 of the neon, where we had the the n equals 2 principal quantum number filling up. And then we jump down to the n equals 3 down here. And so this neon would have been the closest closed shell. And now the only difference between neon and sodium is this extra 3s1 that gets filled up. And so we could rewrite this in the closed shell configuration as neon in brackets and then 3s1. Neon just refers to the fact that everything up to neon is the same, which would be 1s2, 2s2, 2p6. This is the same as neon. And then the only difference here is 3s1. So this is the closed shell configuration. And this is the open shell configuration. They're both correct. This is just shorthand. As you can imagine, as you get further and further down into these really large elements with lots of different subshells, then the notation can get really long and cumbersome. It can be really easy just to write the shorthand version of that, or the closed shell. Okay, so let's think about this circumstance now as we move continually down the periodic table. We're thinking about electron configurations, and we start to move into this realm, into this fourth row. Okay, so this is where it gets a little bit different, but not entirely that different. So let's think about, in this case, we were at n equals 1, n equals 2, n equals 3. And so for the n equals 3 shell, we know that L can take on any value of 0, 1, and 2, and that M sub L then can take on, for each of those, this value of 0, plus or minus 1, and plus or minus 2, depending on its individual value. Okay, and so we also know that L here, this would be s orbital, p orbital, and this would be the d orbital. But we haven't used the d orbital yet. And actually, so if these were our shells, so n equals 1, n equals 2, n equals 3 here, we went from 3s to 3p, but then all of a sudden we jump down to n equals 4. And we're going to use the 4s here. But we still haven't used our 3d orbital, which is this one, our n equals 3 and our L equals 2. And so it turns out this is where that Z effective, that shielding effect, really changes things a little bit. And we get this process called crossover, where we start to fill up our 4s orbital, but then after we've maxed out our 4s, which can only take these 2 electrons up through calcium, now we enter this new block of transition metals, and that's when we start to use the 3d orbital that we'd missed out on previously. So let's think about potassium as an example. So potassium is sort of this easy one. We'll do it as the closed shell form. So the closest closed shell would be this noble gas configuration here, argon, which we can write out like that, argon, and then from argon we jump down and we fill up that extra electron, that 19th electron, and that makes it 4s1. For calcium, we could be the same. Argon is the closest closed shell configuration, and then 4s2. And then let's jump over to scandium. So that's where we're bridging into new territory. So for scandium, it's still going to be argon as the closest closed shell, right? It's still up here, so that's n equals 3. But now we filled up the 4s2 up through calcium, but we've got one extra electron that we need to stuff somewhere. And that's where we drop back down to the 3d level up here, because we haven't used it yet. And we call this 3d1. That's the first that we've added here. So we could go down this row. We could say titanium, similarly be argon, 4s2, 3d2, and we could continue across the periodic table in this fashion. So a good way to remember this is either way. I prefer to just look at the periodic table and I just know that I'm starting at 1s, then 2s to 2p, 3s to 3p, 4s, and then I've got the 3d lined up and then 4p. And you can see that we're always one step below for the 4d, so we go from 5s to 4d to 5p, 6s to 5d to 6p. And so it's like this orange block here is just shifted down one row from the s and the p orbitals, right? So if you think about it this way, you'll always get it right. So you just identify, maybe your elements right here, and then if you want to write the electron configuration, you start up in the top corner where it says begin here, and you keep filling up electrons as you move from left to right and then down a row all the way until you get to your desired element. The other way that people write this is with this configuration here, or this representation. And this is actually kind of handy too. In this case, the way that you can construct this on your own, so you don't just have to memorize this, is just to start by writing a vertical line of 1s, 2s, 3s, 4s, 5s, 6s, 7s, and then I'll change the color here, and then because there's no p orbital here in the n equals 1, we'll just start here as 2p, 3p, 4p, 5p, 6p, 7p, and then we'll do the same thing with the d's. So there's no d in the n equals 1, there's no d in the n equals 2. It starts right here. So 3d, 4d, 5d, 6d, 7d. And let's grab one other color here. So the same is true for the f orbitals. So nothing in n equals 1, nothing in n equals 2, nothing in n equals 3. So we get to 4f, 5f, 6f, 7f. We could do this with the G's as well if we were using those. And now all you do is you start and draw a diagonal line. And the diagonal line, you're starting here. This is your start point. We'll just label that start with filling. Same as the start over here. It's where you start. And then we're going to draw a line through in a diagonal way the first orbital that you're going to fill electrons into. And then when you get through the last orbital here on the left column, then you'll start over at the next side. And so you'll come back up and then draw that through, come back up, draw that through, come back up, draw that through, and you can sort of get a pretty good representation of how these orbitals should fill. And so now you can think about filling these. If you just look at this diagram, either one that we created, 1s is going to fill first, and then if you follow the arrow, the next thing that's going to fill is 2s, and then you follow the arrow, the next thing that's going to fill is 2p, and then 3s, and then loop all the way back around, 3p, and then 4s, loop all the way back around, 3d, 4p, 5s, loop all the way back around, 4d, 5p, 6s, etc. And so both of these, I actually use both of these. If I, sometimes I forget when I'm filling things that are down in the F range or the really high numbers, then this representation is pretty easy for me to remember. If I'm thinking about stuff really in this top level, periodic table is pretty simple to remember as well. So you'll want to practice this quite a bit. It's pretty, you're pretty quick once you've done a handful of these examples. So the Aufbau principle is pretty good, but just like any rules, there's always exceptions in science. And so there are 21 elements on the periodic table that are exceptions to the Aufbau principle, and we call those anomalous configurations. And typically the reason for that is they've got something to do with a half-filled or a fully filled subshell that somehow stabilizes its configuration, and so you get behavior that isn't necessarily predicted by the Aufbau principle. So let's do an example of chromium. So chromium has its closed shell configuration. The closest noble gas configuration is going to be argon, and then below that we've got 4s. And actually, let's pause here for a second. Okay, I just wanted to paste a periodic table so we can see this. So arsenic is all the way over here. This is number 33. And so you can see argon is here. That's the closest closed shell or noble gas before arsenic. So if you go backwards all the way, the next one that you hit is argon. That's why you get this configuration. So after argon, getting to arsenic, we have to go through the 4s1 state, which we do. So there's the 4s, and typically you'd think you'd fill this as 4s2. That's what the Aufbau principle would say. And then you would get to, sorry, I don't know why I'm thinking of arsenic, not arsenic, chromium here. You would have 4s that would fill, and then maybe 3d, 1, 2, 3, 4, right? That would be sort of how the Aufbau principle would tell us to work. But it turns out that's not actually true. So in fact, what we have is chromium, argon, but what you can see is chromium is almost to the halfway point in the D shell. So D has 10 electron spaces right in here. There are 10 spots here, and we were at 3d4 in the Aufbau version. So what this anomalous configuration does is actually takes one of these electrons from the lower energy 4s and shoves it into the 3d, because a half-filled 3d set is actually more stable than what the Aufbau would have predicted. And so instead we get a configuration that looks like this, where this half-filled configuration has 3d5, and this is 4s1. And so this is going to be the case for virtually all of the elements in that are in this portion of the periodic table, because they're one away from being a half-filled set. This will also be true primarily for things in this set, because these would be D9, and adding one more electron would get it to D10, which would be a more stable set, would be a more stabilizing energy than necessarily having the s orbital filled. And so these are some anomalous configurations. I'm not going to have you memorize them, but I might ask you to sort of rationalize things from time to time. So for example, if we did this copper example, copper would have the same closed shell argon configuration, but then it would have a 4s1 and a 3d10. So it's really analogous to chromium here, in that one of those 4s electrons that should be filled based on the Aufbau principle is not, because it gets bumped over to 3d10 to make a nice filled subshell. So one thing that the electron configuration is really helpful for is identifying these things called valence shell electrons. And so when we have something like carbon, which I don't have the actual periodic table here for you, but it's located like right here. Carbon has a closed shell configuration of helium, and then 2s2, 2p2. And so the highest principal quantum number electrons, or those electrons that reside in the highest principal quantum number, in this case these are 2, we call these valence electrons. Everything inside the helium shell would have n equals 1, so we'd consider these core electrons. And sometimes it's helpful to differentiate the two, because valence electrons, those are the ones that are furthest from the nucleus. They're also the highest energy, because they're far from the nucleus, and they have a higher principal quantum number. Because of that, these are typically the electrons responsible for reactivity and bonding. So these are the bonding electrons, and so it's really important, because often when we're thinking about bonding and reactions, the core electrons are safe. they're so tightly bound to that positive interior nucleus that nothing happens. And actually all of the sharing and the giving of electrons that occurs when you make a covalent or an ionic bond, they occur in these outer valence shells. We sometimes call these frontier electrons or frontier orbitals because they're really on the forefront of interacting with other atoms and molecules. And so it's really important to note for valence electrons. This is going to come back tenfold when we get to chapters 7 and 8. All right, so let's do a couple quick examples just to round out this discussion of electron configuration. So what I got here is this this example that states give the ground state electron configuration for arsenic, which has an atomic number of 33, and draw also the corresponding orbital filling diagram. So a couple things to note. Your book and myself and other people will often call the ground state electron configuration. That's just the electron configuration of that element or ion. There are such things as excited state electron configurations, which is the configuration when that element or atom or ion has been subject to some stimulus of energy, whether it's light or something else. We're not going to do any excited state configurations, so this is sort of just a redundant statement. So don't be confused if you hear ground state. That just means draw the configuration. So let's find where arsenic is. It's number 33. It's here on the periodic table. And so I would pause the video if I were you at this point and write out the full ground state configuration, and then maybe write out the corresponding closed shell configuration, the noble gas configuration, and then in addition to that draw the electron filling diagram. So that's using the actual physical electrons to represent those dashes. So pause the video, and then when you unpause it, I'll have the answer worked here. Okay, so what we've got here, looking first at this top example, is we've got the full electron configuration. So we have arsenic out here at 33, which means it's got 33 electrons, which means we got to stuff 33 electrons into those subshells. We start up here as always, and we start by just sort of layering all the different subshells and stuffing 2 electrons into each until we get all the way up to arsenic. And so we've got this top level, this is the n equals 1, so we'd have the 1s orbital filled. That would give us 1s2. This would fill, if we jump down, this would give us our 2s2, and then our 2p6 block, our 3s2, our 3p6 block, our 4s2, which would be this block, and then we have our 3d10, which constitutes this entire chunk here, and then we go to our 4p, but we've only got 3 electrons in this whole p set. So that would give us 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. The shorthand or the closed shell configuration, or sometimes noble gas configuration, we would work backward from arsenic, back up the table, and the next closest noble gas that we see, our closed shell configuration, would be argon. So we have argon, and then we have just our valence shell here, 4s2, 3d10, 4b3. Okay, so the actual orbital filling diagram, I didn't write out the entire thing just to save space. You could if you wanted to. I just wrote out the closed shell configuration. So I've got argon, and then beyond the argon, I've got my 4s2 orbital here. I've got my 3d10 orbital with all 10 electrons, and then I've got my 4p3 orbital. Remember that Hund's rule states that we're going to fill these up one at a time. We're not going to pair them up. They're all going to be spin in one direction. I wasn't explicit about that, but I'll add some arrows there. So they're all going to be spin up or spin down, doesn't matter. And then if I were to add more electrons to say to make selenium, then I would start adding and pairing in the opposite spin state.